start the second talk. It's for Mingchen Xia here. Talk about the Partial Okounkov bodies and partial geometry.
All right, thank you very much for the introduction, and it's a pleasure to be here and give a talk here. But as one of the very few persons who don't work on K-stability in this room, I will only focus on the latter part of this, the theme of this workshop. I will talk about something related to moment maps. And here are the two main references. And in this talk, I will only talk about some general results and without being super precise. So if you are interested in the technical details, you can just look up these references where you can find the precise statements. And in the whole talk, I'll be fixing the following notations. I'll use X to denote a smooth projective variety of dimension n. And more generally, everything in this talk will work on a general normal projective variety as well. And on X, I will fix a holomorphic line bundle, which can be arbitrary, but I also need to require that on L there is a singular positively curved metric. If you are familiar with the notion of plurisubharmonic metrics, that exactly means a plurisubharmonic metric on L. And the existence of H implies that L cannot be arbitrary. L has to be at least a pseudo-effective line bundle. And in the first part, I will talk about some backgrounds. And in the second part, we will begin to talk about the main theme, the partial Okounkov bodies. And before talking about anything, let's agree that in the whole talk, the word convex body will mean a non-empty compact convex set in Rn. And in some references, even in some standard references, people require that a convex body has to have full dimension, but it's not the case in this talk. As already introduced in the talk of Kaveh&ndash, the Okounkov bodies are introduced initially by Okounkov in the special case, and more generally by Lazarsfeld, Mustată and Kaveh&ndash in the more general setting. So the initial given data is simply a line bundle, and starting from this line bundle, they can construct a family of convex bodies in Rn, and the family is parameterized by some parameter nu here, which I will explain on the next slide. And they managed to construct a family of convex bodies canonically associated with the line bundle L. And then the point is, why do we study these convex bodies? The main reason is that Okounkov bodies is a way to translate the geometric properties of the line bundles into the properties of the corresponding convex bodies. As you can see, if we initially were interested in the manifold X and the line bundle L, they are in complex dimension n, so that means real dimension 2n. But if I have translated everything into the convex bodies, they will be in real dimension n. So a priori, they should be much simpler. And the goal of our talk is to construct some similar convex bodies associated with not only L, but also with the singular metric H. We want to construct a similar convex body parameterized by the same parameters nu, which can translate the properties of the pair L and H into the corresponding properties of convex bodies. And these convex bodies will be called the partial Okounkov bodies. And this is a general picture, very sketchy, about the situation, the relation between the partial Okounkov bodies and Okounkov bodies. In general, the Okounkov bodies, although they are not always polytopes, but they tend to be very close to polytopes. But it's not the same case for the partial Okounkov bodies. They are a smaller part inside the Okounkov bodies, but they can be very curvy. Okay. As I said earlier, the Okounkov bodies or the partial Okounkov bodies will be a family of convex bodies parameterized by some parameter. And here is the meaning of the parameter. And this was already explained in Kaveh's talk, but I just put the definition here as a reminder. The parameter can be induced by a so-called admissible flag. And I will not try to explain the word admissible here. But anyway, it's a flag of subvarieties. Here, y0 is a subvariety of the codimension 0, that means x itself, and y1 is of codimension 1, etc., until yn, where yn will be a single point of codimension n, of course. And as explained already in Kaveh's talk, this flag will induce a valuation on the function field of x, valuation of rank n from the function field to Zn. And for example, in the one-dimensional case, we don't have many choices for the flag. The flag only have two components. The first component is x, and the second component will be a single point. So this is the case of the flag in one dimension. We only have the freedom to choose the single point y1 here. And in that case, the corresponding valuation is simply given by the order of vanishing of the rational function along y1. And similarly, this is a picture in dimension 2. In dimension 2, the flag means we choose a curve in our surface and we choose a point on the curve. And the first component will still be the order of vanishing of our rational function along the curve y1. And then after suitably normalize our rational function by the local generator of y1, we could guarantee that this function can be restricted to a rational function on y1. And this is what this bracket does. And then after restricting to y1, we could make an induction and take the order of vanishing along y2. And in this way, we get the second component of our valuation nu. And in higher dimension, it's always the same. It's always the same thing. We want to do exactly the same kind of, we take exactly the same kind of operations, and we end up with a function from our function field to Zn. And this will be a valuation in the sense that it satisfies some natural properties. And the key property is that it translates the product in this ring into addition on this side, on Zn. All right, now we could come back to the construction of the classical Okounkov bodies, which was already explained in Kaveh's talk as well. And the given data is X, L, and the nu, where L is the line bundle and nu is the valuation. Suppose that L is a big line bundle in the sense that it has many holomorphic sections. If you are not familiar with this notion, you could think about something like ample line bundle, which is a special case. And the construction of the Okounkov body can be divided into 3 different steps. The first step is to go from the geometric data X and L into a corresponding ring, the so-called section ring. We consider all sections, all holomorphic sections of L to the k for L power k. And then because L is big, L to the k will have many sections, so eventually this will be a very large ring in general. And the second step, we want to pass from the ring to a semigroup. And in this step, we need our valuation. Recall that our valuation transforms the product into addition. So in this ring, as the ring is closed under multiplication, so we should expect that the result will be closed under addition. So that gives you a semigroup. And the precise way of doing so is as follows. As in this formula, there are several different levels. So the gamma nu L will be a subset of Zn plus 1. It will be a subset of the lattice of one more dimension. And the latter coordinate, the one additional coordinate, will be the level, somehow the level running from 0 to infinity, taking all integral values. And for each fixed level k, we take all of these holomorphic sections, non-zero holomorphic sections, so that we can consider their corresponding valuation. And we put all of these valuations together, and that forms the semigroup inside Zn plus 1. But anyway, this step translates the information of a ring into a semigroup. And eventually, we want to translate a semigroup into a convex body, and this is essentially what the paper of Kaveh and Khovanskii does. So we begin with our semigroup, and we construct its convex hull. Here the notation CONV means the convex hull. It's a subset of Zn plus 1, so you can consider its corresponding convex hull in Rn plus 1. And then we take the piece of level 1 inside this convex cone. So we take such an intersection. And the whole procedure might seem to be a little bit abstract if you have never seen this before, but I'll try to give you a very simple example in dimension 1. We consider X as P1 and L is the line bundle O1, and the flag will consist of a single point 0. And in that case, the corresponding valuation by definition is nothing but the order of vanishing along the point 0. So let's consider how do we construct our gamma nu L. On the previous page, here I have the precise formula. For each level k, we take all the holomorphic sections and take the corresponding valuation. And let's see what are the holomorphic sections here. Our line bundle is nothing but O1. So if we raise it to a power k, that will be OK. And the corresponding holomorphic sections are the polynomials in one single variable of degree at most k. And if you take the order of vanishing along 0, there will be nothing but the integers from 0 to k. So if you put all these points together, you get these red points here. This is the point at degree 0, at level 0, at level 1, level 2, etc. And recall that after constructing the semigroup, the next step is to take the corresponding convex hull and take the intersection with the level 1 set. So here it is, what we do. We take the convex hull of these red points that give you the blue part, the blue cone here, the large cone, and you take the intersection with the hyperplane at level 1. You end up with the interval from 0 to 1. And from this picture already, you can easily see that the Okounkov body, the delta nu L, is a way to characterize the asymptotic behavior of the semigroup as the level goes to infinity. Because if you let the level grows and you take a rescaling of the corresponding points, you get a denser and denser subset of your Okounkov body. And so in that sense, the Okounkov body is a way to reflect the asymptotic behavior of a semigroup. Okay, now let's be more precise about why the Okounkov bodies are useful objects. There are two main theorems in this field explaining their usefulness. The first result was already contained in the original paper of Lazarsfeld and Mustată, which says that the Okounkov bodies delta nu L, although the construction depends on the ring of holomorphic sections of L, but it turns out that the Okounkov body itself depends only on the numerical class of L. That means if you have two different line bundles, and if they have the same intersection number with all curves, then they have exactly the same Okounkov bodies, although their ring of holomorphic sections might be different. And more surprisingly, there is a converse. If you know all these Okounkov bodies for all different valuations, then you can actually determine the numerical class of L. So in some sense, if you are only interested in the numerical class of a line bundle, then you could completely translate every problem into the problems of the Okounkov bodies. Put things in a more fancy manner, then that means the Okounkov bodies, there are some universal numerical invariants of the corresponding line bundles. And as a very simple example, the most famous numerical invariant of a line bundle is the so-called volume, which characterizes the number of holomorphic sections of Lk as k tends to infinity. And this is a very classical result already proved in Lazarsfeld and Mustatı's paper. The volume of the Okounkov body is exactly the volume of the corresponding line bundle up to 1 over n factorial, of course. Yeah.
From that slogan, it sounds like you can also consider intersection of L with canonical device.
Yeah, that's true. We expect that we can do something, but there are no concrete formulas yet.
I guess in the theorem of Joe, it's important that you work with all flags.
Exactly, right. Exactly. If you are working with only a single flag, then this is not true. You have to consider essentially all flags. All right, now we can come to the main part of the talk. We're going to talk about the partial Okounkov bodies. Unlike in the previous part, now instead of only considering X and L, we need an extra information. We need to consider the corresponding. We need to consider the metric, the singular metric H. Recall that H is a positively curved singular metric on L, or a plurisubharmonic metric on L. We put it into the picture, and we want to construct some similar convex bodies delta nu LH, which depends only on the singularities of H, in some sense. And this could be regarded as somehow an analog of the theorem of Lazarsfeld and Mustată. And it turns out that this is possible. And this is the main theorem of the paper I mentioned earlier. These partial Okounkov bodies can be constructed, and they depend only on the so-called I equivalence class of the singular metric H. And conversely, we also have a generalization of the corresponding theorem of Joe, which says that if you know the family of all partial Okounkov bodies for all flags or all valuations, then you can canonically determine your initial singular metric H up to the I equivalence relation. Of course, in order to make sense of the I equivalence, make sense of the theorem, we need to understand what I equivalence means. And this is a notion initially due to Buxton, Favre, and Johnson, and studied in my paper with Tamas Darwas. We say that two singular metrics are I equivalent if they have the same Lalonde numbers on all dimensional models of X. And there are many other equivalence characterizations of I equivalence relation. And roughly speaking, that's a way to characterize, to say that two singular metrics, they have roughly equivalent singularities, like all meaningful invariants associated with these metrics are the same. Okay, so similar to our previous slogan, the partial Okounkov bodies, there are universal invariants, this time not of the line bundle, but of the singularities of the singular metric H. Okay, let's come to the construction. Well, I have already explained our construction scheme in the case of Euro Okounkov bodies without the singularity. The first step is to, given the data of X and L, we go from the geometric data into the ring of holomorphic sections. And the second step, by including the valuation nu, we translate the ring into a semigroup, and eventually we construct a convex body from the semigroup. And now, if we include H, let's see what we can do. Let's try to do exactly the same thing as the first step. So we start from the X, L, and H, and we want to construct something like a ring. So now we consider not all of these L2 sections, but we only consider, not all holomorphic sections of L to the kth, but we are only considering the L2 sections. Here I'm putting I of HK here. If you know the so-called multiplied sheaf, this is that's it. But if you don't know it, that simply means all L2 sections of L to the kth, with respect to the given singular metric. All right, but as you can easily imagine, here we are imposing some L2 condition, but two L2 sections, if you take their product, there will only be something belonging to L1 instead of L2. So this will no longer be a ring. And now we are already in trouble, but let's still try to see what we can do on the next step, in the next step. We want to do exactly the same thing as in the Euro case. So we want to include our valuation into the picture, and we want to construct the corresponding something like a semigroup, the subset of Zn plus 1. So we still take all levels k from 0 to infinity, and we take all corresponding L2 sections of L to the kth. And we put all valuations of these sections together. We end up with something still belonging to Zn plus 1, belonging to the lattice. But the problem is, since in the first step, our object is no longer a ring, so in this step, you can no longer expect our object to be a semigroup. It will be something much more general. And then let's try to think about the third step. We no longer have a semigroup, and we want to construct some object which can characterize the symptotic behavior of your object when the level tends to infinity. What can we do? Here's a picture showing you that the naive approach, what goes wrong in the naive approach. Here, without considering the red point, we have these, without considering the green point, we have these red points. And these red points, of course, they form a semigroup, so you can construct the corresponding convex cone and take the intersection with the level 1, and you end up with the interval from 0 to 1. And there is no surprise, this is a Euro Okounkov body construction. But now suppose that you are no longer considering a semigroup, but you are considering something more general than a semigroup. You add a single point to the picture. You consider the object formed by the red points together with this single blue point, green point. And then let's see what will happen. If you still try to take the convex town, you'll end up with something much bigger, like bounded by the solid blue lines. You get something much larger, and if you still try to take the intersection with the hyperplane at level 1, you end up with the interval from 0 to 4, which is much larger than the interval from 0 to 1. But the thing is, we want to get some convex body which can characterize the symptotic behavior of our semigroup when the level goes to infinity. But you see that with or without the green point, when level goes to infinity, these two objects are exactly the same. So you should expect that they have exactly the same Okounkov body. So even in that case, with with this green point, we still want to get something, we still want to get the interval from 0 to 1. So that means the naive approach by taking the convex tau and take the intersection does not work. Okay, now our two magics, which solve the situation. The first magic is the following observation. Although our object, the ring-like object formed by the L2 sections, is not a ring, but the point is, it's not very far away from being a ring. And to be slightly more precise, this is a theorem. This is a key theorem. This object, gamma nu LH, is an almost semigroup. And if you want to state it in terms of the RXLH, it's also fine. You can say it's almost a ring somehow. And here is an extra word, almost. To make sense of this, the theorem, you need to understand what almost means. But the precise definition is a bit complicated. We consider a pseudo-metric of subsets of Jn plus 1, and this is given by comparing. We consider two different semigroup-like objects, like S and S prime. We consider their level sets at level k, and we compare the number of points inside these two objects and minus by their intersection. And you can show that if you take the lim sup and let k tend to infinity, this object will give you a pseudo-metric on a suitable space of subsets of Jn plus 1. And by an almost semigroup, that simply means that the object can be approximated with respect to the corresponding topology by semigroups. So in some sense, although gamma nu LH is not a semigroup, it's not very far away from a semigroup. That's a key point of the whole project. And I have to also I have to mention that this result is actually super deep and was due to two papers by Tamas Darvas and myself, where we essentially established the theory of volumes for the Hermitian pseudo-effective line bundles. And this is a consequence, essentially a consequence of our papers. Okay, now we can come to the second magic, which is not so surprising if you really consider the definition of the pseudo-metric. The Okounkov body map, initially you can define it only for semigroups inside Zn plus 1, but it means a continuous extension from semigroups to almost semigroups. So what do I mean here? Initially you have a map delta on a subset of this side, on the set of semigroups. And you know that this map is well behaved. You can prove it is well behaved in many senses. But the point is, this metric emits a unique continuous extension to the closure. That means for all almost semigroups, you have a canonical definition of the corresponding convex body. And of course, here we're talking about the continuity. On the domain of definition, we already know there is a topology induced by the pseudo-metric on the previous page. This induced by this kind of pseudo-metric. So we also need a metric on or topology on the set of convex bodies. And there is a natural choice, the so-called Hausdorff metric. And the precise statement means that with respect to the Hausdorff metric and the topology induced by the metric on the previous page, this map is continuous. Okay, let's come back to the pathological example. Initially, without the green point, if you consider only these right points, the corresponding Okounkov body is the interval from 0 to 1. But if you now add the green point here, you get something slightly bigger. But if you consider our definition of the D pseudo-metric, you see that it only concerns symptotic behavior as k tends to infinity. It only compares the symptotic behaviors. So that means adding the green point or not, you end up with something within the same equivalence class. The distance between the semigroup by red points and the object formed by green point and the red points, they have exactly 0 distance. So eventually, eventually by definition, they have the same Okounkov body. So even in this case, by our definition, the Okounkov body of the red point plus the green point will still be 0 to 1, the interval from 0 to 1. All right. Now we can come back to our construction of the Okounkov bodies, the partial Okounkov bodies. In the first step, we construct the ring-like object And in the second step, we translate it into something like a semigroup, but we have already proved that it's an almost semigroup, and we can extend the Okounkov body construction to almost semigroups. So now it comes to the main definition. The partial Okounkov body of L and H is by definition the Okounkov body of the corresponding almost the semigroup here. And it's actually a slightly non-trivial fact, but it's not so difficult to prove that the partial Okounkov body is always contained in the Euro Okounkov body. So now we can finally make sense of the picture I showed you a few minutes ago. On this page, this is the R2 or Rn, and we have a Okounkov body, which is a very large convex body, which tends to be flat in many cases, and we have a rather small part inside the Okounkov body, which can be a bit curvy on the boundary, and that will be our partial Okounkov body. Okay, let me give you a very concrete example, still in dimension 1. Let's see what will happen in that case. We still consider P1 and O1, and nu will be the order of vanishing at the point 0, as in our previous examples. And we have already seen that the Okounkov body of L is given by the interval from 0 to 1. Now let's consider some singular metric, put the singular metric into the picture. We put H here, and suppose that H has some singularity at the point 0. Say the singularity is something like A log Z squared, which is the simplest type of singularity. And in that case, from our very definition, you can verify that the partial Okounkov body is given by the interval from A to 1. So you see it's a part inside our Okounkov body from 0 to 1. And not only that, there is one more important observation. These are a family of singularities, where A can range from 0 to 1. When A is 0, that means there are no singularities, and when A is equal to 1, it has the Euro log singularity. And if we increase A, that means H gets more singular, and in that case, the partial Okounkov body gets smaller and smaller. It turns out that this is a general phenomenon. The more singular our metric H is, the smaller the partial Okounkov bodies becomes.
So in this example, do you get a semigroup, or it's only a...
No, even in that case, it's not a semigroup, I suppose. Let me see. You're right, it's not a semigroup.
So then what does the shape of the almost semigroup look like?
It's almost the same as the semigroup because the difference...
You have the clone, which is the Okounkov body, but then you maybe add some kind of staircase thing.
Yeah, it's true. It's like, let me see. So if you consider the L2 section, there should be some round down construction. If you replace the round down by the round up, that would be the semigroup. So it will be just the slightly bigger than the corresponding semigroup. And recall that we already said in the paper of Lazarsfeld and Mustată, they already proved that the volume of the Okounkov body is equal to the volume of the line bundle. And here's a precise definition. We consider all holometric sections of Lk and normalize by k to the nth, and take the limit as k tends to infinity. And in their paper, they already proved that the volume is equal to the volume of the line bundle. And similarly, for the partial Okounkov bodies, we have very similar things. The volume of the partial Okounkov body is the asymptotic, characterizes the asymptotic growth of the L2 sections. So here we're considering only the L2 sections, so that will be a priori smaller than the right-hand side, and we still take the limit normalized by k to the nth, like k tends to infinity. And it turns out that these two are equal. We can compute the volume of the partial Okounkov bodies. Recall that the partial Okounkov body is a smaller part inside of the full Okounkov body. So if these two guys happen to have the same volume, they should be exactly the same thing. From the expression, you already know when to expect the when to expect that they are the same thing. That happens when, for example, when H has the minimal singularities, and if you know the definition. So as a corollary, when H has minimal singularities, the partial Okounkov body is exactly the Okounkov body. So the partial Okounkov bodies, they are really generalizations of the Okounkov bodies. And here is something that I want to emphasize, which cannot happen in the case of Okounkov bodies. The map from our singular metric to the Okounkov body is a continuous map. To make sense of this theorem, you need to know the topology on H and the topology on delta nu. The topology on H is something defined by Darvas, Dinesa, and Lu, which I'm not going into the details, but it's some kind of topology comparing the singularities between two, comparing the differences between two different singularities.
So sorry, in their paper, is that the metric geometry of singularity types?
Yeah, exactly.
And you take a quotient by I equivalence then to get an induced topology on the space of I equivalence classes of singularity types.
Yeah, exactly. And here on the set of convex bodies, you simply take the Hausdorff topology. And it turns out that this map is continuous. Let me tell you why this is a surprising result if you are an expert in the classical theory of Okounkov bodies. Because there is a famous theorem in the case of Okounkov bodies telling you if you consider all possible projective varieties and all big line bundles on these varieties, you consider all possible Okounkov bodies. These Okounkov bodies, they will form a countable set. So there will be no continuity statement. But in our theory, since we enrich the set of Okounkov bodies to partial Okounkov bodies, the possible types of these convex bodies becomes much, much larger. So that makes the continuity type statements possible. And to many of you, the definition of the partial Okounkov body might not seem to be supernatural, but let me explain to you that there are actually three different equivalent definitions of partial Okounkov bodies. And there's one which is slightly more technical, which I'm not going to present here, but let me show you two other point of views. The first point of view was already contained in the published version of my original paper. Some of you might have already read the first version or archive of my paper, but the result wasn't contained there. And you have to read the published version or the second version or archive to find this result. So let's see what we do. The gamma nu is the almost semi-group. If you still remember, we make a rescaling of our almost semi-group by k minus 1 for some integer k. And we still take the intersection with the hyperplane at the level 1. It might be slightly easier if I draw a picture. Let's say that we have some lattice points. And we consider the subset. For example, our gamma nu might be something like this. And with some additional point, let's say there is an additional point here, one additional point here, something like this. And what we are doing here is we take all points of the gamma nu LH at the level k. So, for example, this is our level k, and we take the convex half of these points. So that, in that case, that will be the interval from 0 to that green point. That will be a very large set, and we make a rescaling of that set to level 1. We rescale it to that convex body, so that will be a convex body in Rn plus 1 in one lower dimension. And now we can let our level k tend to infinity. And one can prove that the corresponding convex halves, they converge to our original partial Okounkov body. This is also a highly non-trivial result. And it is not true. It is not always true for an arbitrary almost semi-group. So that means the almost semi-group gamma nu LH here is special in many senses. If that is not enough to persuade you that the partial Okounkov body is a natural object, here is a second characterization of the partial Okounkov body. The partial Okounkov body of LH is completely determined by the corresponding B divisors. So what do I mean here? If you are not familiar with the notion of a B divisor, let me explain the things to you in the most naive manner. We take all possible resolutions. That means projectives bimorphic map from some projective variety y to x, so that y is a smooth projective variety. And we pull back our L and H to the variety y. And in that case, pi star L will still be a big line bundle on the corresponding variety y, and we can also pull back the metric, singular metric. There will also be a singular metric on the pullback line bundle. And on the pullback part, there is a so-called Xia decomposition. That means we can take out some divisorial parts from the corresponding curvature current of pi star h. In general, this will be a very complicated closed positive 1-1 current, but there is a canonical way to extract the divisorial part due to Xia. And we remove all these divisorial parts, and that will give you some class in the Nihon stability group, and you can talk about the corresponding Okounkov bodies. Okay.
Yeah, no, that's okay.
Yeah. Okay.
Sorry. So there are two news here, and one of them is the long number.
Yeah. You mean here? Yeah. This one? Yeah. I'm not going to explain this. This is some kind of this is a constant vector constructed from nu and h in a complicated way. But anyway, this is a constant which does not depend on the choice of the variational model. That's the point. And this guy is something belonging to the Euro-Nihon stability group, and you can talk about the corresponding Okounkov bodies. This will be the algebraic theory due to Lazarsfeld and Mustată already. And you can consider this algebraic Okounkov body. And the point is, if you let y tend to infinity, then y will belong to a net. If you take the limit of the net with respect to the Hausdorff topology, then you end up with exactly the same thing as your original Okounkov body, but at the expense of introducing some extra vector. And the extra vector is something like the successive order vanishing of h along your given flag, but the precise definition relies on the so-called trace operator introduced by Tamas Darvas and myself in the very recent paper. Okay, so I said earlier that there are 3 equivalent definitions. If you are really an expert, you should expect that there is a third definition characterized using the so-called closed positive currents inside your cohomology class. And the following formula is only supposed to be for the experts. If you can read this, if you can understand the meaning, then this is your third characterization. This will be the closure of the evaluations of all currents where T is a closed positive current in C1L, and T is I more singular than the curvature current of H. This is the third characterization, but that's only for experts. Okay. Now let's talk about some very familiar examples of the partial Okounkov bodies. Although the construction seems to be new, but there are already many known cases in the literature. For example, in the toric setting, then in that case, we're supposing that X, L, and H, they are all toric invariant, and also the flag is supposed to be toric invariant. And in that case, the singular metric, there is a canonical way to identify it with a convex function on the R expansion of the co-character lattice. Here, N is the co-character lattice of the corresponding torus, and R, the subindex R, means that we are taking the tensor product with R, so that this is a vector space R, like Rn. And there is a canonical way to identify the function with the singular metric with a convex function on NR, on R to the n. And in that case, the partial Okounkov body can be canonically identified with the gradient image of the convex function. If you are familiar with the language of Laurent transforms, this guy would mean like the closure of the domain of the Laurent transform of H. And this object has been widely studied in the literature, and of course the importance is already well known to experts in toric geometry. Okay, so finally I have 20 minutes to talk about the applications, which is also an exciting part. The first result is about the slicing of Okounkov bodies, which is some problem widely studied in the literature as well. And it turns out that the partial Okounkov bodies appear very naturally in the slicing problem. So let's see. Initially, we are considering only a line bundle, a big line bundle, and under some very mild assumptions, the intersection of delta L with the part where the first k coordinates are 0 is given by a partial Okounkov body. Still, it's easier to draw a picture. Let me draw something here. let's say that this is our delta L. Oh, yeah, sorry. Can everybody see that? Sure. Okay. Initially, even if you are only interested in the classical Okounkov bodies, and you want to take the slice at the point, say this is the x1 coordinate, you want to consider this intersection. And how do you understand the intersection? The theorem tells you exactly that the intersection is given by a partial Okounkov body. And if you are an expert, this is a partial Okounkov body of the trace operator of the current with minimal singularity in C1, C1L. This result contradicts a widespread result in the literature by Choi, Park, and Wang, where they claim that the intersection is given by an Okounkov body instead of a partial Okounkov body. And their result also contradicts the paper of Zhou. Okay. And right. And more generally, here I'm only explaining the case where you are considering intersection with x1 equals 0. But as here, the same thing makes sense for if you restrict the first k coordinates to be 0, where k is arbitrary.
Excuse me?
Yeah.
Because, from the beginning, you talk about, in this case, you only talk about the big divisors.
Yeah.
But in this paper, it's thinking about the pseudo-effective divisor.
Yeah, that's true. So pseudo-effective is slightly more general than big, of course. The cone of pseudo-effective, the pseudo-effective cone is the closure of the big cone. So it's just slightly more general than the big ones.
I know, but I mean, it is not talking about the size of the big cone. It's a slide. It is the body of the pseudo-effective divisor.
Yeah, that was their first paper. In that case, they defined the Okounkov body of the pseudo-effective divisors. But in their second paper, they studied the slicing problem.
Oh, okay, sorry about that.
Okay, and there's also another result about the interior slices, which was already explained in Kaveh's talk, and this result was due to Kaveh as well. So now if we are interested in the slice of the Okounkov body, not at x1 equals 0, but if we are considering the interior slices, say this slice, and as proved by Kaveh, this slice is still a partial Okounkov body. And this is a very technical result and highly non-trivial depending on the extension theorem, the very strong extension theorems of Kähler currents, etc. And this was the key step in the proof of the volume identity of the transcendental Okounkov bodies, as I already explained in Kaveh's talk. Okay, so this is just a general picture of what we're considering. Let's talk about some other applications of the result about understanding the Lelong numbers in the non-toric situation. Suppose that our evaluation is induced by a flag, say from y1 to yn. Then, if we consider the minimum within the polytope of the first coordinate, if you look at the picture, here's the coax body is a partial Okounkov body, and you take the minimum, that is the minimal distance from between this body and the axis. And the minimum turns out to be equal to the generic Lelong number of h along y1. And the generic Lelong number means the minimum of the Lelong numbers of h along all points of y1. And so from this picture, you can see geometrically how to get the information about the Lelong numbers, etc. And this result even seems to be new in the toric setting. I haven't seen this in the literature anywhere before. And as a very simple consequence of the result about the Lelong numbers, here is a seemingly non-trivial result due to Yi Yao. If in a toric situation, we consider two different toric invariant prime divisors, and we take their intersection. Since we're in the smooth toric situation, their intersection will always be simple normal crossing, so this will be of codimension 2. And we consider the generic Lelong number of h along the intersection. Then, using the previous theorem, Yi Yao proved that the generic Lelong number of the singularity along the intersection is bigger than the sum of the generic Lelong numbers along the two components separately. And let me show you why this is true. Let's still consider the following case. We consider, let's draw everything in the following picture. So here, delta L in the toric setting can be identified with the so-called Newton body, and the partial Okounkov body, as I already explained, is the gradient image of the moment polytope. And if we translate the previous theorem into the current situation, then, for example, the divisor D1 will correspond to a boundary phase of our Okounkov body, of our Newton body delta L here. So, for example, this is the phase corresponding to D1, and this is the phase corresponding to D2. Then their intersection point will be the point corresponding to the intersection of D1 and D2. And using the previous theorem, we can translate the generic little number of H along D1 as the distance between this convex body and this phase. And we can translate the generic little number along D2 as the distance from this convex body to this phase. And just using the toric blow-up, we can show that the generic little number along the intersection point is given by the distance between the convex body and this single point. So now you can already translate everything, the inequality, into the geometric picture, and which turns out to be very trivial. You can prove it within a few lines. For the experts in Archimedean geometry, this is not very surprising. This is only like the local convexness of the corresponding Archimedean potential. So it's not surprising anyway. But the point is, if you use the language of partial Okounkov bodies, it gives you a very geometric way to understand the difference between these little numbers. And you can see from this picture directly where the difference between the little numbers come from. All right, there is a more non-trivial application which has nothing to do with Okounkov bodies, but the proof depends on the Okounkov bodies. Given an Archimedean pre-subharmonic metric on the Berkovich identification of L, and of course here I mentioned something deep, maybe not well known to everyone, so this page will also be for experts only. Given an Archimedean metric in the sense of Buxton and Janssen, there is a canonical way to construct a random marrow on R, which is the so-called Dussel-Hickman marrow. And this kind of construction is already well known in the case of test configurations, which is widely studied in the literature about case stability, etc. And there is a classical way to construct them. And the test configurations, they can be embedded into the space of an Archimedean PSH matrix. And using the theory of Okounkov bodies, we can show that the construction of this random error can be extended to all PSH functions. The interesting point is that the statement is completely independent of the Okounkov bodies, but the proof depends on it. And also, AG explained to me that he also found very similar constructions, leading to essentially the same thing. And the proof consists of 3 different steps. The first step was carried out in my paper with Darvas and Kaveh&ndash, where we translate the Archimedean matrix into some more concrete languages, into the language of complex metrics. So the first step is passing from we identify an Archimedean metric with a concave curve of complex metrics. Here we're coming back to the matrix on our line bundle L instead of the complicated Archimedean things. From now on, we can apply our theory of partial Okounkov bodies. Since we already have a singular metric on L, we can construct the corresponding partial Okounkov body, and the concaveness of the curves can be translated into the concaveness of the corresponding Okounkov bodies. And from these concave curves of Okounkov bodies, there is a construction initially due to Buxton-Chen, or it might have already been known before Buxton-Chen, but anyway, there is a classical construction from a concave curve of convex bodies to a random error on R. And that would be our definition of the partial of the random error. But from the construction, you can already see that it depends on something, although it seems not. But here, when we construct the partial Okounkov bodies, recall that that depends on a parameter nu, depends on the choice of the flag. So a priori, the random error you construct in this way will depend on the flag as well. But the interesting point is, after computing the corresponding moments and using some elementary results in probability theory, you can actually show that this random error is canonical. It depends on nothing. It doesn't depend on the choice of the flag or the valuation. So in that way, we get a canonical construction using the non-canonical Okounkov bodies. And finally, let me mention something. As I have explained everything in the algebraic setting, I'm explaining things like we're considering a projective manifold, we're considering a big line bundle and metric onside, etc. But everything explained in this talk can be extended to the transcendental setting. That means we begin with a compact Taylor manifold, we begin with a big cohomology class, which a priori might not be algebraic. In that case, we can still carry out very similar constructions based on the joint work with Thomas Darwas, Rémi Reboulet, W. Winstrom, and Kaveh Zhang. Before ending the talk, I want to tell you a conjecture which I have been interested in since many years ago. Basically, no progress has been made in that direction. There are, as you can see, there are two different versions, but the first version, again, is still supposed to be for experts, since it mentions something technical terms like I-good metrics. But these two conjectures should be equivalent, and the second conjecture is a special case of the first conjecture. So let me explain only the second conjecture to you. Assume that L1 to Ln, there are big line bundles on your projective manifold. N is the dimension of the line of your manifold. And then the conjecture is that the movable intersection number from L1 to Ln is equal to the supremum of the mixed volumes of the corresponding Okounkov bodies, where your nu runs over all flags or all valuations. And this is the movable intersection number, like introduced by the famous VDPP paper. I'm omitting some normalization, like 1 over n factorial here, as you can easily insert it either in the definition of the movable intersection number or in the definition of the mixed volume. If you consider the case where L1 and Ln, they are all equal, then this is nothing but the result already obtained by Lazarsfeld and Mustată. And in the more general setting, since we have the Joss theorem, which tells you that if you know all Okounkov bodies, then you know the numerical class of L1 to Ln. But the point is the movable intersection number depends only on the numerical class of L1 to Ln. So in principle, there should be a formula relating the movable intersection number with the family of all Okounkov bodies. And here is my precise conjecture. And I like the case of I like the homogeneous case where the line bundles are all the same. In that case, we don't need a supremum. But in that case, there is a counterexample due to Chen Jiang showing you that without the supremum, this is not true in general. So I still expect that with the supremum, this is true. And this is a conjecture for or an exercise for all of you.
What is the notation on the right-hand side? Is this the supremum?
Yeah, supremum of nu of the mixed volumes.
Mixed volumes. Okay.
Yeah. All right, and that's all. Thank you.